Get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We were starting a new topic last time. I left the handout in the file for you guys. Okay, so it's working. So now we're going to go through it. The next topic is related rates. It's one of those application topics. Make sure I can see the chat here. Okay, so for the second test and the final, there will be a bunch of word problems that you have to do. And this is one of those problem types. By the way, exponential growth and decay was another one of those problem types. Things like optimization is another one of those problem types. Curve sketching would feel like one of those problem types, but this is one of them. So it's one of the applications of derivatives that we like. Marginal analysis is another one. And they come to us in the form of word problems because you want to describe some sort of real world situation which you're going to use calculus or something that was derived from calculus to figure out. So the first, I guess, really big one is related rates. And that's what we're going to do. Now, I would have written out everything that is on this handout. So I'm just not going to do that. Just going to sort of read to you in the beginning, point out the important things for you to pick up on. This is on the class website. As you guys know, it's also going to be in the class notes. And it was on the class notes for last class. So you'll have these notes. Technically, you don't really need to write anything down, but I will make a note of what the important things are. So the first paragraph is just kind of explaining what related rates actually means. The idea behind this is, as we know, we can use calculus to track rates of change of things we care about, right? That's one of the things we can do with it. But sometimes we just don't have enough information to do that. However, we have information about something else that's related to the thing that we care about. And we might even know the relationship between the thing that we care about and that thing that we have all the information on. And the idea is, how can we use something that's related to the thing I care about to determine information about the thing I care about, right? So like rates of change, etc. And it turns out that is actually, once you know the relationship, that's actually pretty easy with implicit differentiation. It turns out that whenever quantities are related, their rates are automatically related. Related in the mathematical sense means that there's a mathematical formula that you can write down that connects the two things. Now, once such a formula exists, you can literally just differentiate through that formula, and you would get a bunch of rates of change of the dependent variables, and you'll be able to use the rates of change of one to talk about the rates of change of the others. And so that's the kind of idea. We are going to be using related rates, hence the name, to find rates of change of quantities that we care about. Okay, so that's basically the idea. And when it comes down to it, the thing that you really need to know is to recognize when you're reading a word problem, here or in life, if it ever comes up, the things you need to really understand what kind of problem it is. And that's here. So this part is very important. How do you know you're looking at a related rates problem? Well, it turns out that there will be a couple key things in the word problem that's going to indicate this to you. So one is it's going to be, you're going to be told about these related quantities. You're going to be told about several things that either a relationship between them is described, or it's just obvious that there's a relationship between them. Like they might talk about the length and the width of a rectangle. Obviously, there's a relationship there. The area and radius of a circle or something like that, right? Obviously, there's some sort of relationship. You can come up with formulas that connect these guys. And so they'll describe these quantities to you, and they'll give you some information. They'll tell you about one or several of these things, how fast their rate of changes are, how fast they're changing, and they'll ask you about the rate of change of the other one. So they'll say something like, well, you know, the length and width of a rectangle is, the length is changing at this rate and the width is changing at this rate, and then they'll ask you about something related, like how fast is the area changing? In fact, I think that's one of the problems, right? But that's just to give you an idea. So in that problem, they have the length, the width, the area. These are all related quantities for a rectangle. I can come up with an equation to connect all three of those things. And then they tell you about some of them and ask you to find the rates of change of the other one. So that's the basic premise, right? So those are the two things. They're going to give you something here like, oh, quantities A and B are blah. They're related in this way. I know quantity B is changing at this rate. And then they're going to tell you, find out how fast quantity A is changing, right? Once you see a problem type like that, it's a related rates problem. So you're going to be told about quantities and related rates, and you're going to be asked about some other rate, right? So when it comes to the different types of word problems, you really want to understand what would hint to you that you're looking at a certain type of word problem. So we already looked at exponential growth and decay. We looked at the keywords that would indicate that you're looking at such a problem. But there's no real key word for related rates. It's just like a key type of question. Where you're described a bunch of things, you're told some rates, and you're asked to find another rate. When that's the case, it's a related rates problem. Now, the moment you recognize it's a related rates problem, there are 6 steps for you to go through to solve such a problem. And these 6 steps are important. Muy importante. And of course, by the time a test or a quiz comes around, I will expect you to have memorized these steps. Although not memorized everything in this table, I elaborated in this table a lot because I want to explain the idea behind each of the concepts, and we are going to do this so you'll see it more clearly. But at least what I have in bold, you should have those phrases memorized, kind of know what to do first, second, third, fourth, fifth, sixth. And that would be expected. So you should definitely know this table. So first, you're going to read the problem carefully. Students don't read enough. They don't read carefully enough. Case in point, on the first test, I gave 5 points for writing down your name. And there were actually people who missed those 5 points because they didn't read the problem carefully or whatever. So don't let that happen to you. Read the instructions. Always be aware of what the rules of the game are that you are playing. So you want to read carefully. Not only do you need to read it to know that it's a related rates problem, but you'll have to pick out the important pieces of information that you'll need in future steps 2, 3, and 4 specifically. And you really want to know that it's a related rates and you have all the values that you need. The second thing you want to do after reading the problem and understanding that it's a related rates problem, the second thing is to draw a diagram. If it's possible to draw a diagram, if it's necessary to draw a diagram. And here I kind of describe to you when it's possible or necessary. Did I? Well, I described to you how to label it. I would say the diagram, not necessary. Pen is a little too thick today. I would say the diagram, not necessary. If the relationship is given. Right, so the relationship as in the equation that's going to govern the situation that you're talking about. The diagram is very helpful because it helps you visualize the situation. You know what it is that you're looking for. You know what it is that you want to find. You know what it is. You know what time it is, right? You know everything, right? So the diagram is going to help you to kind of figure out a relationship. So that's how you would want to, when you want to sketch a diagram. Now, it's very important how you label the diagram because there are mistakes that can occur when you label a diagram incorrectly. So you do want to label the diagram with any parts of the diagram that are changing. they're maybe growing or shrinking over time, you want to label these with a variable. And anything that's not doing that, you want to label it with a constant, right? It's going to have some fixed value, and you want to label it as such. But yeah, that's the way we should label the diagram. And I'll probably show you why that is important later on. The third thing you're going to do is just set up a goal. You're going to write down the information that you know and the information that you want to find. And at that point, you can actually forget about the original word problem. You're not going to care anymore. You don't have to confuse yourself with the words. You're just going to kind of zone in on what you actually want to accomplish. Once you've done that, you are going to set up an equation that relates all the quantities that you have been described. If you draw a diagram, it usually comes in handy here. So you will be able to, if you see that it's a circle and the area and radius are described, then automatically the formula would come to you, oh, a equals pi r squared, right? Things of that sort. So you're going to set up an equation that relates all the quantities that have been described before. So this is going to be the equation that you're going to use. And yeah, as it says here, if your diagram is a triangle, you would think about Pythagoras' theorem or similar triangles or things of that sort. So the diagram can suggest to you what formulas you want to use. Once you have a formula, you move on to the fifth step. You're going to differentiate implicitly with respect to time. It is always with respect to time. T is always going to be the independent variable for a related rates problem. It's always how fast they're changing over time. So that means, what the implicit differentiation means, well, we know what that means. Every time you're differentiating something that's not the independent variable, you will multiply by the prime of that variable, okay, by the chain rule. And then 6, the final step, somewhat, 6 can actually break up into 2 parts. Is to just plug in all the values that you know and then solve for the values that you want to find, right? So information is going to be given to you. You're going to want to be able to input that information and then find information that you want to find. Now, there's one potential hiccup that can happen here. Sometimes you'll get to step 6. Did I mention that? Like I originally tied this up in spring 2019, as you can see. So I might have forgotten what I written and not written back then. Plug in your knowns, solve for the unknowns that you seek. At first, you may end up with several unknowns. Okay, yes, so I did write it. So a potential issue in step 6 is you might get to step 6. You might plug in everything you know in step 6, and you might have several unknowns. There might be 2 or more things that you still don't know, and you're like, I can't solve this. I only have one equation, and there are a bunch of unknowns. Like, how am I going to actually do this, right? So whenever that happens, what you do is you panic. I'm kidding. You don't panic. Don't panic. That was a joke. You are going to go back to step 4. So step 6, sometimes you should be able to go back to equation 4 and solve for the unknowns that you don't have, right? And we'll do examples where we have to do this. Okay. So that's the only kind of potential issue with step 6. The potential issue with step 2 is not labeling your diagram correctly. And I've had a lot of students get in trouble because they didn't label things correctly. Okay. Once you kind of get up to step 4, I don't see a lot of people making mistakes after that point. But the original setup is going to be important. And I do see some people falter in step 6 at times. That's it. Something else you need to know. Oh, yeah. 2019 Jhevon did write that down. The point of drawing the diagram is to be able to visualize a problem. If you're given that equation, you don't need to a visual aid, so you don't need to draw the diagram. He thought of everything, that guy. Yeah. This guy must know what he's doing. Okay. All right. Those were the steps. One other thing that I would say you should know is to just be aware that for a problem type like this, you are expected to kind of know about certain geometric formulas that you would have gotten from geometry, like Pythagoras' theorem, area of a circle, circumference of a circle, area of a rectangle, perimeter of a rectangle, things of that sort. Some basic geometric things. Things like volume equations, volume of a box, finding the volume of a prism, or that's when you have one shape and it's just elongated along some axis. You should know how to find the volume of that. It's the area of the base times the height. Yeah, things of that sort you'll be expected to know. So you might want to brush up on those things as well. So what we're going to do here is I've selected some problems that I want to go through with you guys. So that's 1, 3, 4, 5, 8, and 10. Don't want to spend too much time on that. We're probably going to spend too much time on these as well. But I actually want to get related rates done this class. So we'll see how that works out. And we'll move on. So tons of examples. You're going to notice that I'm always going to be using this 6-step process just to kind of hammer, drill it in, that this is what you do, this is how you organize your thoughts, this is how you get through this problem. Yeah, so we're going to do a bunch of these. And whatever I don't do, you can try on your own. And let me know how it goes. I do suggest that you practice way more than is required. The thing with these word problems is it's just really practice in knowing what you should do at each step. The things you have to differentiate tend not to be as difficult as something that I would ask you to differentiate in a direct differentiation question. If I just say, oh, here's this random formula, differentiate it. That might be a challenging problem because I'm going to check if you know the rules and you know how to combine rules and things of that sort. But in word problems, that's usually not the case. You don't have this big complicated formula to differentiate. So the calculus isn't the hard part for these guys. It's just knowing the process, knowing how to get through them. Okay. Yeah. So without further ado, let's get to the examples. Hopefully that was clear. If it wasn't clear, it should be clear after I go through a couple examples. Okay, so let's get through. Okay, been rambling for a while. It's time to get started. A right circular cylinder undergoes expansion. Trying to conquer the world. Its radius is increasing at a rate of 1 meter per second. Its height is increasing at a rate of 2 meters per second. At what rate is the volume changing? When the radius is 1 meter and the length is 3 meters. Okay, so classic related rates problem, right? You're told about several related quantities, the radius, the height, and the volume of a right circular cylinder. You're given information about the rates of change of the radius and the height, and you're asked about the rate of change of the volume, right? So that's classic related rates. Several related quantities are described. You're given the information, the rate information on several of them, except one, the one that you care about, and you're asked to find that. So once you read that, you know it's a related rates problem. In fact, step 1 is to read. It's an important step. Reading is fundamental. 2. So now that we have read, we are going to want to draw a diagram. Okay. I want to put the questions up on the other screen here. So I don't have to be scrolling back. You're going to draw a diagram. Well, it's a right circular cylinder. So okay. So there you have that. I would label the things that are changing R. I would also label H, the radius and the height. And I'm going to say V equals the volume. Right? You can't really see that on the diagram. The volume is how much space the thing takes up. Okay. So that is my fully labeled diagram. Right? This is a right circular cylinder. So 3, once we have that, we're going to write down what we know and what we want. Write down the given information, write down the information you want to find. What do we know? What do we know? Radius is increasing at a rate of 1 meter per second. So dr dt, remember t is always the independent variable, is 1 meters per second. The height is increasing at 2 meters per second. So I also know dh dt is 2 meters per second. Now there is something that might not be shown here, but I do want you to pay attention to it and appreciate it because it might come up otherwise. Remember, we saw that increasing means the derivative is positive, decreasing means the derivative is negative. We are told here that these guys are increasing. So me writing down this 1 and this 2 is not as straightforward as you might think because the sign actually matters here. Turns out here that the fact that this is a +1 and a +2 is very important. There are times when I would make one or both negative based on what's described. So this plus is because they're increasing, right? That is why you read. You need to pay very close attention to how things are changing, not only what things are changing, but how they're changing. Is it increasing? Is it decreasing? Because you're going to have to make a sign change. So you're reading very carefully. You're setting up your diagram. You're labeling it very carefully. And you're writing down what you know very carefully. Now, what do we want? At what rate is its volume changing? Right? So we want dv dt. When do we want it? Now, no, we want it at a specific instance when the radius is 1 and the length is, the height is 3. Okay. So that's what we know, and that's what we want. And this is our diagram. Now, it turns out that once we've written down these equations and drawn this picture, you actually don't need it to even look back at the word problem anymore. We know what we want. We have all the required information, and we can just continue. So in step 4, we are going to come up with the diagram. Not the diagram, the equation. The relationship. Okay. So now the diagram should help you with that. You've probably seen that diagram before in high school geometry class. You're starting to have, PTSD. You're just back and forth. No, I don't want the ruler. Okay, so that's going to kind of indicate to you what formula you want to use. You'll notice it's a prism. It's a right circular cylinder. You just have a circle being stretched along the length h. So the volume is going to be the area of the base times the height. Okay, so we have our equation. We move on to step 5. We are going to differentiate our equation. We're going to differentiate implicitly with respect to time. So, all right, help me out here. How do I differentiate this with respect to time? Go, someone tell me what the answer is going to be. You guys can't have me doing all the work. I'm the only one who has to be awake at 8:30. I don't think so. Come on, wake up my sleepy babies. I see you. I see you.
No, I'll be
okay. Good. All right. Come on. Tell me. Hello? Someone said
I said I have honestly have no idea.
You have no idea. Okay, all right. Does anyone have an idea? Let me ask this. What are the dependent variables? Do we know what the dependent variables are?
Is that R and
Oh, let me ask it the other way. What is the independent variable?
isn't that time?
That's time, right?
Yeah,
Which means,
H dependent.
come again?
Are RH dependent?
Yeah, but there's another guy.
Oh, and I guess pi.
No, pi is a constant.
No, not
The V,
volume.
right?
Yeah, yeah.
Yeah, literally every variable besides t is thought of as a dependent variable. They're all functions of t. We just don't really know what they are. So yeah, so now you're differentiating that whole equation with respect to time. What is the derivative of v with respect to time? Okay, so I have y, and I want to take the derivative with respect to x. What do I get? Remember when we did that lesson with implicit differentiation?
Or you get y prime.
You just get y prime, right? You get y prime or dy dx, right? Yeah, so what do you get when you differentiate v? Well, v prime, right? dv dt. In this setup, I like to remind myself that the independent variable is t. So I use the Leibniz notation whenever doing this. I think it's nicer to use Leibniz notation here. Because usually there are a bunch of variables swirling around, and you do want to keep reminding yourself t. T is the independent variable, t, right? You might even have an x in there, and you're just so used to differentiating with respect to x that you end up just differentiating with respect to x. You do not want that. T, it's always t, right? So I always switch to the Leibniz notation for related rates just to, remind myself it's t is the guy here. All right, so how do you differentiate pi r squared h? Remember, pi is a constant. So you can essentially just leave it alone. How do you differentiate r squared h? Anyone? Bueller? No? We all asleep? Okay. All right. So I guess I need to say this now. Review implicit differentiation. It's super important. This is, in fact, an application of implicit differentiation. Okay. All right. So what we would do here is notice that there are two functions of t. So we would use the product rule. And so I'm going to differentiate one, leave the other. plus leave the first, differentiate the second. There is something missing. Do we know what's missing? From the first term?
A prime.
A prime? Which prime?
R prime.
R prime. I just differentiated R, so I need to multiply by dr dt. In the second one, I differentiated the h. I need to multiply by dh dt. Okay, it's very important that you remember the differentiation you're doing is implicit differentiation. If you're not differentiating a t, you need the prime. And again, I know like the majority of times I'm talking about derivatives in this class, I will use a prime, but I would recommend, it's a soft recommendation, that you write it in terms of dv dt, dr dt, dh dt, like Leibniz notation. Okay. So this is one situation in which I'd probably prefer you to say, oh, I should multiply by dr dt as opposed to say r prime. Yes, they're the same thing, but I think it's nicer to think of it one way as opposed to the other. And there are times when some stuff like that becomes very, very important, but that's like calculus 3. We don't really have to worry about it. Now we can just be like, oh, prime this, prime that, and we can just go about our lives. That gets kind of tricky. Eventually, calculus gets complicated enough where the Leibniz notation is really what you should use almost all the time. Yeah, but that's it. You do the product rule. If you're differentiating and you have a product of functions, do the product rule, but you also remember I'm differentiating with respect to time. Time is the independent variable. So every time I differentiate something that's not a t, I have to multiply by d of that thing over dt, right? I have to multiply by the prime. So that is differentiating the equation. Okay. Now we move on to step 6. We're going to plug in. Okay. So at this point, we want to plug in everything we know and solve for what we want to find. Now, remember, this is the guy we want to find. He's already neatly tucked away on one side, so that's nice. We can just copy that back down, dv dt. Now on the other side, we're going to start plugging stuff in. At this point, we need our information. We go back to what we know and what we want to find. We know that dr dt is 1 and dh dt is 2. We also know that I care about the situation or the instant where r equals 1 and h equals 3. So I want r equals 1, dr dt equals 1, h equals 3, dh dt equals 2. So I go and I plug that in. R equals 1, h equals 3, dr dt equals 1, r equals 1, there's no h, and dh dt equals 2. That's that. And this guy I'm going to ignore because I can. Okay. And now what do we have? We have 6 pi plus 2 pi. So this means your dv dt is 8 pi. And it would be like meters cubed per second. At least, I mean, generally, I won't really care about the units. If this were a physics class or a chemistry class, or any class except math, like I would care that you know the units. But yeah, if you get the number, I'm happy with it. You should just realize that it's increasing at 8 pi cubic units. So that's the problem. Notice we're going through the 6 steps. We read carefully. We had our diagram. We labeled it carefully. Write down what we know, what we want. We set up an equation. We differentiated that equation. And then we plug in what we know and solve for what we don't know. And every related rates problem, you're going to use these 6 steps. Every related rates problem in this class, you're going to use these 6 steps. It can get a little bit tricky otherwise. Okay, so hopefully I knocked some of the rust off our brains. This one should go by a lot smoother. In fact, whenever I want to do something productive, I should switch to the Windows machine because it's actually, for some reason, very difficult. Make it a little smaller. Okay, so here's the third example. Okay. A 15-foot ladder was resting against a vertical wall. Suddenly and without warning, the foot of the ladder slides away from the wall at 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? Okay, so we read this problem. We know it's a related rates problem. How do I know it's a related rates problem? I'm told about related quantities. How far up a ladder is on a wall, how far away the foot of the ladder is from the wall, and I'm told that the foot of the ladder is moving at a certain rate, and I want to know how the top of the ladder is moving, what rate at which that is moving. So it's definitely a related rates problem. Cool. 2, diagram. What diagram here you guys think? What would be a nice diagram here?
Well, wouldn't you want it to show like the ladder falling, which would kind of make it more of like a triangle type thing? I don't know.
Triangle, right? So a triangle, yeah. So you'll notice here, you would have the wall, right? And you'd have like the ground, and you'd have that ladder leaning against the wall, and then you'll have the ladder, right? And then you basically see, oh, hey, that looks like a triangle. So that's going to be your diagram. It's a triangle. What kind of triangle? What kind of triangle is this?
A right triangle?
It's a right triangle, right? So there's a little choop right there. It's a vertical wall. Now, the fact that it's a right triangle, now a lot of equations should automatically be popping up in your head. So we're already kind of getting our mind working on step 4. However, before we get there, we have to label this diagram. How would you label this diagram? Give me some variables. What do you guys want to do? So I might give you some variables in like a test so that everyone kind of looks the same. So let's say I said X is that length, because it kind of reminds me of the X and Y axis, and Y is that length. What would you use for the hypotenuse?
Wouldn't you say 2 feet?
2? 2, where? Here?
Yes. Because isn't it a 2-foot ladder? Unless oh, 15.
No,
15. I'm sorry.
15. Yeah. The 2 was something else. You
Yeah, that's the amount it's
15.
falling.
Right. Not a variable. It's a 15-foot ladder. It's not going to change, right? What is changing is the length along the ground, because we're told that the foot of the ladder is moving in this direction, which means that the top of the ladder is moving down in that direction. So the X and Y lengths are changing. However, the ladder itself is not changing. It's a 15-foot ladder. It'll be a 15-foot ladder even after it falls down. I'm going to label that with a constant. Okay? So that is the diagram and the proper labeling. Now, if you had said something like Z, then there's a potential problem that can happen, especially if you're not paying attention. If you're paying attention, you'll probably be able to get over it anyway. But most students don't pay enough attention, or just when they're in a test, they're just so anxious they don't really think about it. Yeah, so that's the diagram. Third thing, we're going to write down what we know and what we want. What do we know? The foot of the ladder is sliding away from the wall at 2 feet per second. So if the foot of the ladder is going in this direction, right? What that means is that the length x is increasing. So I know that dx dt is plus 2 because that length is increasing. That's all we're told. What do we want? We want how fast the top of the ladder is sliding down the wall. When do we want it? Now? No, we want it when the foot of the ladder is 9 feet from the wall. So x is measuring the distance that the foot of the ladder is from the wall. So it's, in other words, we're just saying when x equals 9. Okay. So that's the third step. The fourth step is to come up with the equation. What equation do you guys think for this diagram here?
You use 1/2 base times height.
And that would give you what? 1/2 x times h. What would that give you?
The area.
The area. Do we have any information about the area?
No.
Yeah. So
No.
probably don't want to use that. Another formula for that would apply to this triangle.
Pythagoras Theorem.
Pythagorean theorem, right? So Pythagorean theorem, notice that the only information we're given in this problem is a bunch of lengths, right? The length of the foot of the right triangle, the length of the height of the right triangle, the length of the hypotenuse of the right triangle. There is an equation that relates all these lengths, Pythagoras' theorem. Right? So we're using the diagram to help us. Like the area, we're not given any information and it's not really there. So unless they told me information about the area specifically, I wouldn't use the area. I'm only told about length. So Pythagoras' theorem. I know x squared plus y squared must be 15 squared. All right, moving right along. 5, we're going to differentiate implicitly. All right, what would the derivative look like? Quickly. Derivative of x squared is what?
2x dx dt.
Correct. Derivative of y squared similarly is 2y dy dt. Derivative of 15 squared?
Zero.
0, right? It's a constant, right? And here is the potential issue. So this is why I type in the notes, label things that are constant by constants, because then you'd realize that the answer is 0 right away. If we did, let's say x, y, z, then we set up, x squared plus y squared equals z squared. And then we went through and we differentiated 2x dx dt plus 2y dy dt equals 2z dz dt. A lot of students get confused by this. Right? So they're in a test and they would come to, oh, professor, I think you didn't give us enough information or something like that. Or they just get stuck at this point and they're like, I don't know what to do with this. My parents are going to disown me. I'm going to fail. I'm never going to get into med school and my life is going to be ruined. Yeah, all of that happens because of this like one stray letter right here. It's sad, really. You don't want that, right? Now, of course, this isn't a problem since dz dt is 0 because it's not changing. The thing is constant, which means it has the rate of change is 0. Let's move this down a little bit. But the thing is, in a test, when the chips are down, no one remembers that. They just see this as this extra variable that they can't figure out what it is, right? Which is it's not great. Worse, some students just make up a number and put in here. If we label with a constant in the first place, we never end up with this issue. Okay, so that's where it's come from. Yeah. So that is what we get when we differentiate it. Now we move on to 6. We're going to plug in. This is the guy we want, the dy dt. That's the guy we care about. Notice that we know we want this when x equals 9. We wrote that down. We also know that x is changing at a rate of 2 plus 2. What is y? So we have y dy dt here. This is the guy we want. But this guy, what? What is that? We have 2 unknowns here. What do we do when that happens?
You panic.
No, you're remembering the wrong thing.
You go back to step 4.
You go back to step 4. Once I realize that, hey, I don't have enough information, I go back to step 4. Okay, so I'm going to go back to step 4. What is step 4? Step 4 had that equation. Step 4 says x squared plus y squared equals 15 squared. And I know that my x is 9. So now I have an equation that has y in it as the only unknown. I can now find that y. Notice what I have here is 9 is 3 times 3. 15 is 3 times 5. That should remind you of a little thing back in high school geometry as well. You guys know what I'm talking about? What kind of triangle is this? Has a name? Well, it's called the 3, 4, 5 triangle. You have these guys called Pythagorean triples, numbers that always show up. 3, 4, 5 is one of them, a very popular one. You can also have things like 5, 12, 13. You know, that's another popular one, and a whole bunch of other things. But yeah, so in other words, you can know that this means your y is going to be 3 times 4. It's actually proportional, so it's going to be 12. Or you could solve for it, or you could solve y is equal to the square root of 15 squared minus 9 squared, and then you work that out. But in theory, you're not using a calculator on an exam, so that would be very annoying. But you could do it. Square 15, square 9, subtract it. You'll get 144. You take the square root of it. You'll eventually get to 12. But it's nicer to just notice, hey, that's a 3, 4, 5 triangle where all the sides are multiplied by 3. And so y equals 12. So now you can go back. So you have 2 times 9 times 2 plus 2 times 12 times dy dt equals 0. Okay, so now you have your dy dt is going to be equal to, I'm going to move the 2 times 9 times 2 to the other side, and going to divide by the 2 times 12. The 2's would cancel. 2 would go into this 6 times. So I have minus 9 over 6. I can take 3 into each of those, minus 3 over 2. And it's feet per second. Notice the minus 3 over 2. It is negative because y is decreasing. So something that occasionally happens here is that a student would get to this point and they're like, well, y is a length, and I don't know if I can have negatives there. And they just, for no reason, remove the negative. The negative is supposed to be here. And if you didn't get a negative, you would be making a mistake, right? Because here, clearly, if the hypotenuse is not changing and the foot is getting longer, the height has to get shorter, right? Like the ladder is going to slide down the wall. And it even said that in the problem. So your y is actually getting smaller while your x is getting larger. So your x is going to have a positive rate, your y is going to have a negative one. But once again, notice we went through those 6 steps. You read, you draw a diagram, write on what you know, what you want, come up with an equation that relates everybody. The diagram might help with this. You'll see that diagram, you'll notice it's a right triangle. Hey, Pythagoras Theorem, or area of a triangle, or, well, for us, we don't have trig, so you wouldn't think of like SOHCAHTOA or something like that. But generally speaking, SOHCAHTOA would be something else that you would think of whenever you see a right triangle. These 3 ideas should immediately pop into anyone's head. And then you set up that equation, you differentiate. Remember, you're differentiating with respect to t. So even your x, the derivative of x squared is not 2x. It's 2x, x prime, 2x dx dt. And then you plug in. Occasionally, you don't have enough information. You don't panic. You just go back to step 4, solve for that guy. Then you come back to step 6 and continue. And then you can get the answer that way. Okay. right. All right, let's do this. Be a little better. All right. The volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is its radius increasing when the radius is 2 feet in length? The volume of a sphere of radius r is given by this formula. So we're given the formula. 1, read. I know it's a related rates problem. Good. So I know I should be jumping into the 6 steps. 2, diagram. Here, not necessary. We're given the equation. They told us right here. 3, what do I know? What do I want? So I know dv dt. And I want to know, I know dv dt is 5, yeah. And I want to know how fast the radius is increasing when the radius is 2 feet in length. So I want to know dr dt. When do we want to know? When r is 2. Yeah, that's it. That's what I want to know. And 4, now we move on to the equation. 4/3 pi r cubed. So then we move on to the 5th step, differentiate. So we're going to have dv dt equals 4 pi r squared dr dt. And I want to know dr dt. So I want to know this guy when r equals 2. So now I'm going to move on to step 6, plug in. dv dt, I know is 5, 4 pi r is 2. Yes, r is 2. So now my dr dt is going to be 5 over, that's 16 pi, 4 times 4. And that is, I mean, it's not important, but feet per second. Okay. There it's go. Now, you want to get to a point where you can do a problem relatively that quickly. I mean, on a test, or I would expect you to take 10-ish minutes max on a related rates problem. But a lot of them, if you've really studied enough, they should actually take less than that. But yeah, that's the process. Here, we didn't need the diagram because we're given the equation. Okay, let's make this one a little bigger. Okay, the side length of a cube is increasing at a rate of 2 inches per minute. When the side length is 3 inches, A, how fast is the surface area changing? B, how fast is the volume changing? So there are 2 separate problems here. So let's do A. Step 1, you're going to read. Step 2, you're going to put in a diagram. The diagram would be, well, it's a cube. Let the side length be x, x, x. And we can set A equals surface area. So we move on to 3. What do we know? Am I writing smaller than I did before? I am. Can you fix that here? Okay. What do we know? What do we want? We know that the side length is increasing at 2. So we know that dx dt is 2. We want dA dt when x equals 3. Yeah, that's for part A. Now we don't even have to look at the word problem anymore. So 4, we're going to go with the equation. Surface area is just the length of all the faces. Area of all the faces. Or sum of. So we know that the surface area is going to be, well, x squared is going to be the area of each face, because a cube is made up of a bunch of squares being back to each other. And there are actually 6 of them, right? The front, the back, the left, the right, the top, the bottom. So there are 6 x squares. I could have told you that this was an open box, in which case it would be 5x squares, but you reading the problem, would you pick that up? So that's our equation. 5, we're going to differentiate with respect to what variable? T, always T. So dA dt equals 12x dx dt. Move on to 6, we're going to plug in. What do we want? The dA dt. We want this guy. When do we want it? When x is 3 and dx dt is 2. Yeah. So that means your dA dt is equal to, what is that? 12 times 3 is like 36, so that's 72. And that's inches per minute. Inch squared per minute for this area. Okay. So there's another problem. Again, the 6-step process. Read, diagram, what you know, what you want to find, equation, differentiate, plug in. Always the same thing. For B, well, B starts out pretty much the same way as A, actually. So the first 3 steps are going to be very, very similar. Okay, so we're going to read. That's our diagram. In this case, we don't care about surface area, we care about volume. The rate and the length x are the same, but here I just want dv dt. Going down to step 4, the equation. I know that v is just going to be length times width times height, because it's a prism, area of the base times the height. Area of the base is x squared, the height is x cubed. 5, going to differentiate. So this is dv dt equals 3x squared dx dt. 6, going to plug in. We want dv dt. So dv dt is going to be 3 times our x was 3, dx dt was 2. So this means our dv dt is 9 times 2. No, 27 times 2. 54 inch cubed per minute. Now, this one is somewhat tricky, but as I'm going to tell you the trick for a problem like this, you'll be able to hopefully do something similar. At noon, ship A is 80 miles west of ship B. At this time, both ships set sail. They set sail at noon. Ship A sails south, speed is 20 miles per hour. B sails north, speed is 10 miles per hour. How fast is the distance between the two ships changing at 2 p.m. if both ships maintain constant speed? Okay, so again, it's a related rates problem. 1, I read it. Definitely smells like related rates. All right, so now 2, diagram. Now the diagram is the first challenge here. Once you get a nice diagram going, you will be able to kind of figure out what's going on. So here I would say, all right, here, right? So this is 80 miles right here, right? Going from here to here. A is west of ship B, so that means A is over here, B is over here. All right. They both set sail. A sails south. So A starts moving in this direction. B starts moving in this direction. Okay. Now, they are traveling until 2 p.m. So now you'll notice that there comes a point where this is B at 2 p.m. and this is over here, A at 2 p.m. We'll ultimately need to know the lengths of these guys. So if B is traveling north at 10 miles per hour, how far will it be after 2 hours? Anyone?
40 miles?
It's B is 10
B,
miles per
sorry,
hour.
I was looking at A. Sorry, 20 miles.
Yeah, so this is going to be 20 miles. There's a very funny YouTube video about this, about a guy in the car with his girlfriend, and he's making fun of her. And he's like, okay, so if we're traveling 80 miles an hour, how long will it take for us to get 80 miles? I don't know if she was faking it, but she couldn't figure it out. Here, ship A sails south at 20 miles per hour. So after 2 hours, 20 miles per hour for 2 hours, you'd travel 40 miles. And what are we asked about? How fast is the distance between the two ships changing? Now, whenever you say the distance between things, in math, it's always the straight line distance between two things. So we want this here. So now I can just start putting in some variables. Suppose I call the length that A travels X, the length that B travels Y, and the length that I care about between them, Z. All of these are changing, therefore they're all labeled with variables. And you might wonder, man, this is like two right triangles like flipped on each other. No, we can actually fix this by putting in our own corner. And so this leads us to the diagram. That's just one big right triangle, where this here is Z, this part here is X plus Y, because it would be the B length plus the X length. And this part here is going to be 80, because they were 80 miles apart and they're traveling vertically. So the horizontal distance is not going to change. So we have that. That's our diagram. 3. What do we know? What do we want? I know how X is changing. We know that dx dt is 20. We know that y dt is 10. We want dz dt when at 2 p.m. Right, so that's when our X is 40 and our Y is 20. Okay. All right, so yeah, that's what we know and what we want. 4, equation. So we created a right triangle here, so Pythagoras' theorem. We know that the sum of the squares of the length and base is height and base is going to be the square of the hypotenuse. So 80 squared plus x plus y squared equals z squared. 5, going to differentiate. Derivative of 80 squared is 0 because it's a constant. Derivative of this guy, 2 times x plus y times the derivative of the inside, dx dt plus dy dt equals 2z dz dt. And this is the guy we want. So now, so 10 is the last example, but I'm actually going to leave that for you guys. We'll start next class by that, because I want you guys to work on something on your own and kind of like figure it out. Sometimes related rates, it's hard to learn it in one class. You have to just go home and let it sink in and try some stuff. So try a bunch of problems, but at least try problem 10 for next time. So now we're going to plug in. We know x is 40, y is 20. We know dx dt is 20, dy dt is 10. And we know 2z, z is, oh, I don't know what that is. So we don't panic, go back to step 4. I know that 80 squared plus x plus y squared is z squared. X plus y is going to be 60. This is 20 times 4. This here is 20 times 3. So this must be 20 times 5 by 3, 4, 5 triangle. So I know my Z is 100. And so now back to 6. We have 2 times 40 plus 20, that's 60, times 20 plus 10, that's 30, equals 2 times 100 times dz dt. Now dz dt is the only unknown. We can solve for it. Two times 60 times 30 over 2 times 100. 100 would go get rid of the 10s, the 2s would cancel, and I would just have 3 times 6. Miles per hour. And that's that problem. Try this for next time. Make sure you understand this process. But hopefully you see, it's always the same 6 steps, right? So even in this rather complicated one, maybe this is like a final problem, final boss. You read, diagram, write down what you know, what you want to find, equation, differentiate, plug in. If plugging in, you don't have all the information, go back to step 4, find the information you need, come back to step 6, right? All the problems, we sort of went through this scenario, and that's kind of what I want you to get, like this protocol going, this, all right, related rates, read, diagram, what you know, what you want, equation, differentiate, plug in. Related rates, read, diagram, what you know, what you want, equation, differentiate, plug in. Oh, related rates, read, diagram, what you know, what you want, equation, differentiate, plug in, right? Oh, related rates, read, diagram, what you know, what you want, equation, differentiate, plug in. Read, diagram, what you know, what you want, equation, differentiate, plug in. Like it's going to be, it should be, it might take a while to write things out, but this should not be a problem that you're confused about on a test. Like you shouldn't be, oh, what should I do again? Like the moment you're like thinking about what your next step is going to be, you're done messed up. Okay, you're done messed up. You're already going to take more time than you should, because these 6 steps are how you do it, right? At least in this class. So yeah, we are going to stop there. Try this for next time. It'll be in the notes. It's also in the handout on the class webpage. If you scroll all the way to the bottom, click on the related rates handout. But try this problem, try a bunch of the other ones to try to get into that groove of going through these 6 steps. And yeah, you should be fine. So we'll stop there. That's related rates. We will finish up that last example next class, and then we'll get into max and min values, absolute max, absolute min, relative max, relative min. And after that, we'll be able to do curve sketching, I think will be the thing after that. So that's that. You can read up on max and min values like also if you have time. But until then, I will bid you guys adieu. I will see you guys in the next one. Ciao.